Okay, this is under the lab portion of the pendulum lab. I just wanted to show you this, maybe not as much for the physics for the math, but just the math for the math. So I'm going to start this pendulum starting first, still on the slow motion, and that pendulum next, and then you can kind of see the motion of what's going on here. Okay, I've also turned the period timer on. So I want to try to find out what the period of, I believe the blue one is first. So we can see that it's drawing the period and it won't stop it until it's gone through a full cycle. Okay, so this is going to tell me what the length of the period of the blue one is. Now this is not the normal speed, so I'm going to turn it back on. That's what the normal speed looks like. But sometimes it's hard to understand it when it's going in normal speed. So I'm going to slow it back down. And I'm going to start the period for this thing, or it starts for itself. I'm going to switch it to the red and see what the period for the red is. Now, I could see the potential of how you could give multiple groups different like parameters for this particular pendulum problem. And then this would be a very good like challenging problem to get them to start to talk about how you can relate circular like motion to periodic motion. Okay, it's nice you can get that particular thing. You could write that down. You could it certainly would help you in the determination of how you're going to write your periodic function. And then maybe when we put the stopwatch on from where maybe where it reaches the high point, we could pause it up there. Now I know I missed the high point, but knowing when it's back at the baseline would be important. Knowing when it's at its maximum will be important for one side. And then back at the origin there. And then you can see it almost makes that there if I'd have been right on time. So I'm going to reset that again. And then this time we're going to try to pause it at the top. Right there. Okay, it's paused at the top. Now, they're both kind of like at the beginning of a period or in a part of their period. Typically in math and physics, to the right is supposed to be positive, and to the left is negative. So if we're thinking about what a sine curve would look like, I think this would be either at the maximum of a cosine curve, or to begin the period, or like a 90-degree shift on a sine curve. All right, now if what I'm thinking is accurate is true, then you should be able to see a connection between the when it hits this dotted line right here. So I'm going to try to pause it right when the red gets there. Oh, it's just a little bit past it. Okay, that's about a fourth, a little bit more than a fourth at that point. I'm going to try to pause it at the top, right there. If you look, that's about half of the period. Okay, so this should be about a fourth when it comes back down here, right about there. So that's like 3/4. I'm going to try to pause it at the top. All right, that's pretty good, like approximations there. So that can show you like what it basically means to have a period, which is a pretty powerful like discussion topic that's not directly related to a sine curve, but you can help you like translate it into a sine curve. Now this ruler, it's nice to be able to use this ruler whenever you'd like it, but it gets in the way when you're watching it swing, so I'm going to turn it off. Now let's see what's up with this velocity vector. Okay, I still like this in slow motion because it's easier to understand. All right, you can see as the velocity reaches, as the pendulum objects reach to the top, the green arrows stop pointing up, and they get to 0, and they start pointing down. Okay, and they point in the other direction until they get to basically the top, and they do more of the same. All right, And what's going to happen eventually is these things are going to be pretty close to like being at the same place at the same time, despite the fact that we swung them up in different areas. That also can be a helpful fact for us when we're building our functions and trying to like make sure we understand what's going on. All right, um, that's velocity, which is certainly changing as the pendulum swings. Now, since acceleration is really contributed to gravity, and we assume that the gravity's acceleration is constant, then it is not shocking that my yellow arrows, or some would say vectors, are the same length, but just changing directions. I think there'd be an interesting discussion about why it's completely vertical and hits the midline, and why it switches directions once the pendulum hits the maximum or the minimum. Those are all good things. Um, what you're noticing now is I would think that eventually these things, they go on forever because I don't think that these are going to stop moving because there's no friction involved. Now, in a math class, friction is just way too many variables for us to be able to deal with. So that would be something I would leave for the physics teacher to discuss. So I might not even do the velocity and the acceleration. I certainly, if we look at these energy graphs, I wouldn't even venture to try to pretend that I could explain that in a meaningful fashion to a group of students there. Potential kinetic energy. It's starting to remind me why I'm a mathematician and not a physicist. Okay, these are all great applications of like this pendulum problem. All right, I just wanted to add that to our particular like presentation so you could see how well they could be. It's easily modified into a gaming type scenario. All right, thank you for watching my video.